Hello and thanks for watching. This next video in my series of videos on grade 11 physics is designed for my grade 11U physics students from Ontario, Canada, and it deals with the concept of local gravitation and universal gravitation. The video is also designed to illustrate the difference in similarities between each of these. Since the video was made specifically for my grade 11U Introduction to Physics course, and as such was recorded with the students in mind, you may find that if you are from out of province or not one of my students, that some of the conventions and formatting requirements may not apply to you. However, it is hoped that you will find this video to be beneficial. Thanks very much for watching, and here we go. The term local gravitation, as I'm going to use it, refers to the effects of gravity acting on an object nearby another object. Specifically for this course, we look a lot at objects such as yourself and your proximity to the Earth. It may be some other object near a moon, near Mars, or some other planetary body. On the other hand, the concept of universal gravitation, which both Cavendish and Newton had a hand in, concerns the force of gravity or the effects of gravitational fields between any two masses and at any two distances between their centers. Thus, for large bodies such as moons and planets, it is very important that you factor in the radii of those planets or moons. There are three significant aspects to the law of universal gravitation that need to be talked about. The symbol that we use is the force due to gravity, or F, the vector, sub g, capital G, although small g can be used interchangeably, because ultimately they do mean the same thing. It is the force of gravity between bodies, or acting on bodies, is equal to a constant g, which is referred to as the universal gravitation constant, and two masses, m1 and m2, and this is divided by the distance between the centers of mass of the two masses m1 and m2. What is important to note here are the relationships between different variables, specifically in this case, the force due to gravity and the masses that are involved. In this case, we can see that the force due to gravity, F sub capital G, is proportional to the product of the two masses as long as the distance between the centers remains constant. In a similar way, the force of gravity is proportional to the reciprocal or inverse of the square of the distance between the centers, provided the masses of the two bodies remains constant. Another important feature of this equation is the symbol capital G, which represents a constant, and it is known as the universal gravitation constant. It's a very important number. The value for G to two decimal places is 6.67 times 10 to the exponent 11 in magnitude, units newtons times meters squared divided by kilograms squared. The value of this constant suggests that the gravitational force is extremely weak, as indicated by this 10 to the minus 11 exponent. If we look at two masses, m1 and m2, and the distance between these two masses is 1 meter, and the masses have a mass of 1 kilogram apiece, then the force of gravity between these two masses is 6.67 times 10 to the minus 11 newtons of force, which is very, very weak. In the world of, for example, static electricity and electrostatics, the equivalent value for G would be 9.00 times 10 to the 9th Newton Coulomb squared, the value or the unit for charge, divided by, Newton meter squared divided by Coulomb squared, the Coulomb being the fundamental unit of charge in electrostatics. So let's see how we do the mathematics of this particular problem or situation. We have somebody here hanging in space, whose mass is 64 kilograms. And since we're dealing with different masses here, we'll refer to this one as mass 1. We also have to deal with the mass of the Earth, since we are looking at the interaction between this body, this person, attached to a Newton spring scale, and the Earth. We're going to have the person, for this problem, at an orbit above the Earth equal to 100 kilometers. What we need to do is find out the force due to gravity between these two bodies. Okay, so let's begin by writing out the main equation, the topic sentence as I refer to it. And the topic sentence here is, simply going to be F sub G is equal to G M1 M2 divided by the distance between the centers of mass squared. Now, we have to pay particular attention, in this case, to the meaning of M1 and M2. And in fact, since we are dealing with the Earth, we can call one of them the mass of the Earth. So what we typically do, remembering to line up equal signs, having a good area in which you're working, logical and well laid out, will help you solve more complex problems in physics. So I'm going to rewrite this as G M1 mass of the Earth. Again, your teacher or perhaps websites you visited might denote this some other way. This is not a universally accepted way of indicating the mass of the Earth. There are many ways. And that will be divided by the total distance between their centers squared. At this point then, it's a matter of substituting in the values for these different variables. So let's continue. Throughout this video, it is a good idea if you have a calculator with you and that you try to do some of the work ahead of time, pause the video, do some stuff on your own, use your calculator, start the video up again and see if you're on the right track. So we line up our equal signs. We'll get our pen here. We line up our equal signs and we now substitute in our known values. So as I mentioned before, the value for G is 6.67 times 10 to the exponent 11, and the units are Newton meters squared divided by kilograms squared, and that will be times the mass of the person. In this case, I've chosen 64 kilograms just arbitrarily. And that will be times the mass of the Earth, which you can look up anywhere and find that it is 5.98 times 10 to the exponent 24 kilograms, a rather massive body. And all of that is divided by r squared. Now, the important thing to remember here is that when we're talking about r squared, we're talking about the total distance between the object, the person, here, and the center of the Earth. So we do have to factor in the radius of the Earth, and we must add to that the height above the Earth that the object is at. So the total distance is the radius of the Earth plus the radius of the orbit. Well, the radius of the Earth, once again, you can look that up in the back of your textbooks or online. It's 6.38 times 10 to the 6th meters. We want to add to that, because we're above the surface of the Earth, 100 kilometers, or 100,000 meters, or if you want to use scientific notation, 1.00 times 10 to the 5th meters. All of that is squared. One of the big mistakes that students make is they do forget to square the radius at the end. So it's important for you to remember to square the radius. So if we do these calculations in our calculator, and I have a calculator here that I can show you. Move it up here so you can see this one. 6.67 times 10 to the minus 11. Putting that into your calculator. For those of you in my class, you can go to my Blackboard website and you can click on the video that shows you how to use some of the other features of your calculator beyond just adding, subtracting, multiplying, and dividing. For now, though, I'll show you what. This is not an active calculator, but I'll show you what you would do. You would hit 6.67. Now, this is the key for this calculator that allows you to enter exponentials or scientific notation, that is, times 10 to the something. Yours may be different. Yours might say ENG on it, or EXP, or some such thing as that. You will have to look that up in your book that came with your calculator, or ask somebody how to do that. So I will then I will type in 6.67, and then on my screen, when I hit this button, I will then see a 10, and it's waiting for a number. And in this case, I will hit the plus minus button because it is a negative exponent, and then I will type in 1, 1. And then I will successfully enter this value in. I now hit the multiplication sign, and once again I enter times 64, and I enter this number, 5.98 times 10 to the 24 kilograms, in a similar manner, 5.98 EE, and I will then be given it something. Again, your calculator may be somewhat different, but an option to then enter an exponent. Please remember that in scientific notation, you do not type in, for example, 5.98 times 10. This button does the base 10 and the exponent for you. So really, this button here gives you the times 10 to the 24th if we're talking about the mass of the Earth. So keep that in mind. So when I complete the calculations on the numerator of this equation, I find out that I end up with 2.25527 times, as you can imagine, a fairly large number, 10 to the 16th. And the units are interesting. The units are Newton meters squared, sorry, Newton kilograms squared. So newtons times kilograms squared, Newton meters squared, kilograms squared. Divided by kilograms squared. And all of that is divided by the sum of the two radii that I mentioned before. So when you add 6.38 times 10 to the 6 meters to 100,000 meters, you end up with, and square it, you end up with 648,000 meters squared. You can imagine the numbers are big, so it's very important to make sure you're using your calculator properly. So now it's time to do the division. Perhaps this number is still in your calculator. It is a good idea sometimes to make use of your memory function buttons. For example, here, the button to store, and that way you can store a previous long calculation and recall it so that you don't have to re-input everything. Just is a bit of a time saver. So if we go through and we do that math, we find out that we end up with, this was 648,000 meters squared. That was the sum of these two. I hadn't squared yet. So we have 2.25527 times 10 to the 16th. Now you'll notice that we have kilograms squared on the numerator and kilograms squared on the denominator of this. And so our units that we're left with are Newton meters squared. I think you can see that it's important to manage your quantities, manage your units, keep your area clean, line things up, make your numbers big, give yourself some space, otherwise you'll find that mistakes will happen. When I take this number and square it, I end up with 4.19904 times 10 to the exponent 13 meters squared. Don't forget the unit is also squared here. And once again, I see that I have a similar unit on the numerator and denominator, and they cancel. And I should be left with newtons because, after all, I am finding the force due to gravity, or sometimes it's referred to as the weight, and you'll see this sometimes, W, the weight, the force of gravity being your weight relative to, for example, the Earth. So now it's a matter of simply carrying out the division, again, being aware of your exponents, and we find that the force of gravity comes out to be 537.0918 newtons of force, and to the proper number of significant digits, I end up with the force due to gravity is equal to 64 had 2, so 5.7 rounds the 3 to a 4, 5.4 times 10 to the 2 newtons of force. And that would be the force of gravity acting on you if your mass was 64 kilograms and you were at a height of 100 meters above the surface, kilograms, above the surface of the Earth. Okay, now let's see what the force of gravity acting on you or some person would be if you were on the surface of the Earth and you were hanging from a Newton spring scale. What would the reading be? Well, now we're in the realm of local gravitation because you are on the surface of the Earth and near to the center of mass of the Earth. So the relationships we've developed previous to this showed us that the force of gravity that acts on a body, you or some other object, is directly proportional to your mass, provided that G, the gravitational field strength vector, is constant. So for Ottawa and at our altitude, so this is a function of latitude and altitude. For where we are, G is equal to 9.8. Now, you might look at this number and say that resembles G that we used for the acceleration due to gravity, and certainly in magnitude it is. However, we're going to define G slightly differently this time. Instead of referring to it as meters per second, we are instead going to define it in equivalent units of newtons per kilogram. It's left up to the student to demonstrate that a newton per kilogram is dimensionally, or in terms of units, equivalent to a meter per second per second. We also realized that the force due to gravity was directly proportional to, well, it would seem as though for some strange reason there's a glitch with my software here, so I will have to voice dictate from here on in what to do. There's very little left. This is actually the simplest situation. It was the universal gravitation that is much more difficult for most students, so I did get through that. So the force of gravity will be directly proportional to the gravitational field strength, provided the mass remains constant. When we put these together, we end up with an equation that says that F sub G is equal to M times G. So that's a fairly simple, straightforward multiplication. You take the mass of 64, so you would type in 64 multiplied by 9.8 and hit enter. or equals, depending on what your calculator looks like, and up will come up the answer, which will be 627.2 newtons. And when you round that off to two significant digits, it becomes 6.3 times 10 to the exponent 2 newtons. It is an interesting activity to try the following, and I would ask you to try this. If you go back and look at the equation for universal gravitation that we first looked at, you'll see that this equation indicates that mathematically you should multiply the constant, 6.67 times 10 to the minus 11 newton meters squared per kilogram squared, times the product of these masses divided by the distance between the centers of mass squared. I leave it to you as an exercise to solve this portion right here, where m1 will, g times m2 over r squared, or g times me over r squared. So try that. Multiply g times me and divide it by the radius of the Earth only squared. Don't factor in the extra 100 kilometers. Just this times this divided by the radius of the Earth squared. And see what number you get. The number, the magnitude of that number that you get should look familiar. So thank you very much for watching. I do apologize for the last 2 or 3 minutes, but there are sometimes technical errors with software that can't be avoided. Like I said, the big thing was I wanted to get through an example of using the Universal Law of Gravitation. Thank you very much for watching.